So today we will take the application of this BE statistics or Bose-Einstein statistical distribution function. In that, there is a derivation of Planck's law of radiation. You can derive the Planck's law of radiation using this Bose-Einstein statistical distribution function. And basically, the Planck's law is applicable to photons. What do you mean by photon? Photon is a particle having particular energy, and there is a quantization of energy in case of photon. Photon means it is a packet of energy. It represents the light. Okay, so light is having certain frequency of radiation, so that the energy of the photon is given by E equal to h nu. So where h is the Planck's constant, nu is the frequency of radiation. There you can find the basic Planck's law of radiation, but basically the quantization of energy is represented in different form, and that is what we are going to do in today's class. So Planck's law of radiation we will try to derive. So we know that this BE statistics is applicable to indistinguishable particle, the particles which are not having the difference between them. For such particle, you can apply this Bose-Einstein statistical distribution function. Let us consider the perfectly blackened enclosure. Okay, a perfectly blackened enclosure means the radiations cannot enter the enclosure and they cannot leave the enclosure. That is the meaning of blackened enclosure, because a black body absorbs all the radiation, and also it will emit the radiations of the absorbed frequency of same radiation as that of the absorbed. Okay, you can study the black body radiation. There you can find the meaning of blackened enclosure. Let us take volume of the enclosure is V, and that is filled with radiations and which is kept at a temperature capital T. That is the absolute temperature of the system. So basically the system which is having radiations whose volume is V and temperature is maintained at temperature T. Okay, that is the concept we are considering here. So radiation is basically considered as collection of photons. Radiation is nothing but photons, and these photons are completely randomly moving inside the system, and they have the unit spin. The spin of the photon is unity, and they obey Bose-Einstein statistics, because Bose-Einstein statistics is applicable to particles having integral spin. Then I can find the number of photons with energy between E and E plus D, which is given by N of E dE equal to G of E into F of E into D. What is N of E? It is number of particles having the energy E. G of E is the density of state or number of available states with energy E. F of E is the distribution function with energy E. Okay. Here, this density of state is already known to us, and here F of E is actually Bose-Einstein distribution function, because we are studying photons. For photons, Bose-Einstein distribution function is applicable. So using this, you can find out what is the number of photons present with energy E. That can be found using this expression by substituting the density of state expression and the Bose-Einstein statistical distribution function. So we have Bose-Einstein statistical distribution function F of E is equal to 1 by e to the power alpha plus E by kt minus 1, where alpha is undetermined multiplier, E is energy of the state, K is Boltzmann constant, E is the temperature of the system. Okay, F of E we know. Then we can substitute this F of E in the expression. You will get the number of particles with energy E, that is N of E into dE, that is given by G of E, that is density of state, divided by e to the power alpha plus E by kt minus 1 into dE. So just we have substituted F of E, that's all. Okay, so 1 by this term we have substituted here. Then density of state. What is the density of state corresponding to momentum between P and P plus dP? Already we have discussed in one of the previous classes. The density of state G of P into dP is given by total volume of the system divided by h to the power F, where F is degrees of freedom. In this case, it is a three-dimensional space. That's why degrees of freedom is 3. So total volume by volume of the one phase cell into the volume of this particular sphere, because in momentum space the states are represented by means of spheres. So therefore the volume of that hollow sphere is 4 pi p square into dp. That is volume of the sphere having outer radius p plus dp and inner radius p is given by 4 pi p square into dp. That is surface area of the sphere, that is 4 pi p square into thickness of the sphere, that is dp. Okay, that is total volume of the sphere, which is containing the energy state between the momentum p and p plus dp. Once you get that, you can find the total density of state by considering the polarization of the photons, because for each photon there are two independent directions of polarization. So in a given state you can find two photons, one with one transverse polarization and another with the other direction polarization. Okay, so polarization means it is a process of confinement of electric field in a single direction, polarization of light. So photons are having two independent polarizations, therefore they have two allowed momentum states. In a given momentum state you can find two photons. That means two photons may occupy the same state, but they differ by their direction of polarization. So two photons can be observed with same momentum, but their polarization is different. Okay, it is just like spin of the electron. Spin of the electron you have studied. Only electron can have upspin or downspin. Two different spin orientations are possible. Similar to that, for photon, two different polarizations are possible. Because of that, the density of state is twice the above equation, 2 times of that of the particular density of state. This is the density of state representing number of states. In each state, two photons are occupying, two photons are allowed. Therefore, the total density of state will be 2 times this particular term. Therefore, you will get a total density of state G of P into dP is equal to V by H cube into 8 pi P square into dP. Okay, so total density of state in momentum space. Okay, that is found here. Now let us consider the energy of the photon having frequency nu. So energy of photon having the frequency nu is E equal to h nu. That is the expression for energy of the photon, where h is the Planck's constant, nu is frequency of radiation. Okay, then for photons, momentum in terms of wavelength lambda and frequency nu will be given by, so what is the expression for momentum p? Momentum of the photon p can be expressed in terms of lambda by using the de Broglie hypothesis. Okay, so you might have not studied de Broglie hypothesis. De Broglie hypothesis says the wave nature of the particle. Okay, so wave particle duality, that will be studied in quantum mechanics. Okay, basically de Broglie hypothesis appears in study of quantum mechanics. But for time being, you remember, you believe me, momentum of the photon is given by P is equal to h by lambda, where h is the Planck's constant, lambda is the wavelength of radiation. Okay, so that is given by h nu by c, because we know that lambda into nu is equal to c. Therefore, 1 by lambda is equal to nu by c. So you know the expression for velocity. Velocity c is equal to frequency into wavelength. C is equal to lambda into nu. Therefore, 1 by lambda is equal to nu by c. So I have substituted for lambda here. Okay, so nu by c is the expression for 1 by lambda. So momentum p is represented in terms of energy h. This is h energy of the photon. Momentum is directly proportional to energy h nu by c. That is how you can express momentum in terms of frequency of radiation, where c is the velocity of radiation in vacuum, velocity of light in vacuum. Okay. Next, to find the expression for dP, what you have to do, you differentiate this by taking h and c as constants. H and C are constant. Therefore, we'll get dP is equal to H by C as it is. Derivative of nu is d nu. Now you substitute for P and dP in the above equation. In this equation, you express P in terms of nu and you express a dP in terms of d nu. Okay. Then you will get a density of state in frequency space as a function of frequency. Now substituting for P and dP in the equation, G of P is equal to V by H cube into 8 pi P square into dP. If you express this, the density of states with the frequency between nu and nu plus d nu. What you have to do? You have to convert the momentum coordinate into frequency coordinate. We have to express the density of state as a function of frequency nu. Then you substitute for P. So P is h nu by C, 8 pi into P square, V by H cube as it is, 8 pi into P square is h nu by C the whole square. dP is h by C into d nu. Just substitute. Then h square, h cube that gets cancelled. 8 pi V will remain, C cube will remain. So C square into C cube, and nu square, frequency square will remain. So Planck's constant H gets cancelled, and you will get the density of state in terms of momentum coordinate nu, G nu is equal to 8 pi V divided by C cube into nu square into d nu. Okay, so this is density of state corresponding to the frequency coordinate. So let us take the application of this density of state to the photon. If the enclosure is at constant temperature, the walls of the enclosure will absorb and re-emit the photons continuously. Okay, so what will happen? The inner surface of the enclosure is perfectly blackened. They may absorb the photon and they may re-emit the photon continuously. Therefore, the number of photons in the enclosure cannot be constant, so that the number of photons will going to vary, because some of the photon may be absorbed and later after some time they may be re-emitted. But in the derivation of distribution function, Bose distribution function, it was believed that the number of particles is constant, and we have multiplied the Lagrangian multiplier alpha minus alpha to the conservation of number of particle expression, so that alpha must be 0, because the dni, the summation of dni cannot be 0, because that is not constant, that is variable, and therefore minus alpha in the Bose-Einstein statistical distribution function must be 0 for photons. So corresponding photons, the value of alpha is made 0. Okay. So therefore, what will happen to the expression? Basically, this expression you can recall, we have added this term to the Bose-Einstein distribution function, minus alpha into summation of dni equals 0. We believe that this dni is 0, where alpha is non-zero, by deriving the Bose-Einstein distribution function. But for photons, in case of photons, what will happen? This number of photons inside the enclosure is not constant, it is variable. So dni is non-zero, it is not equal to 0. Change in number of particle is finite. There is a change in number of photons. Therefore, this is not 0. This equation is, however, true. Therefore, this alpha must be equal to 0. Okay, that is how you can make this alpha 0 in case of photons. So substitute this alpha equal to 0 in the equation. You substitute for g of nu, and also you substitute for f of nu, that is distribution function f. Then you can get the number of photons frequency between nu and nu plus d nu will be given by n of nu into d nu is equal to g of nu divided by e to the power e by kt minus 1 into d nu. Okay, so we have to substitute for this density of state in frequency space, because we have tried to find out the number of particles having the frequency nu instead of energy E. So substitute for E, you will get n of nu d nu is equal to 8 pi v divided by c cube into nu square into d nu divided by e to the power h nu by kt minus 1, because energy E is equal to h nu according to the concept of photons. So basically this is called as the number of particles or number of photons having the energy between nu and nu plus d nu. Okay, having the frequency between nu and nu plus d nu. So finally, you can get what is the energy density. That is what the Planck's law of radiation says. Energy density of the radiation is quantized. Okay, so discrete energy is observed for radiation, for photons. That is basically the concept behind the Planck's law. So once you find the number of particles, you can find the energy density. That is energy per unit volume of the enclosure containing the photons of frequency between nu and nu plus d nu. And that is given by energy density epsilon nu into d nu is equal to total energy divided by total volume into number of particles having that particular frequency. So total energy of one photon into number of photons, that will give you total energy of the group of photons divided by total one. Okay, you got this point. E is representing energy of one photon. N of nu represents the number of photons having the frequency nu. Therefore, energy per unit volume is given by total energy divided by volume. This E into N of nu gives total energy, and therefore you will get epsilon nu d nu is equal to energy is h nu by V, and N of nu we have just derived, that is 8 pi V divided by c cube into nu square divided by e to the power h nu by kt minus 1 into d nu. That is energy density. Okay. So finally, you collect all the terms, you will get energy density is 8 pi h divided by c cube into nu cube divided by e to the power h nu by kt minus 1 into d nu. So this is called as Planck's law of radiation, which states that the energy of radiation is discrete. Okay, it is not continuous, whereas it is going to be discrete. You can find what is the energy density inside the volume, that depends on the total number of photons into energy of each photon. If you calculate the energy density, you can find that the energy inside the system of photons is going to be discrete, that cannot be continuous. So this is how you can derive the Planck's law using Bose-Einstein statistical distribution function. And this was given by Sir S.N. Bose in 1924, and it is called as Bose statistical derivation of Planck's law. Okay, so S.N. Bose is Indian scientist who has provided or contributed for the derivation of Planck's law using his statistical distribution function. Okay, so it was done very long back, that is in 1924, and this Planck's law of radiation can be derived using Bose-Einstein distribution function also. This is how you can derive the expression for energy density as a function of frequency. Similarly, you can express this energy density in terms of wavelength also. That also will try to complete today. So Planck's law can be expressed in terms of wavelength of radiation also. And we know the frequency of radiation nu is given by c by lambda. We can express this frequency coordinate into wavelength coordinate. So nu is given by c by lambda, and therefore d nu is given by c by lambda square into d lambda, because the lambda is variable, frequency nu is variable, while velocity of light is constant. Okay, derivative of 1 by lambda is 1 by lambda square. Therefore, derivative of this equation gives you d nu is equal to c by lambda square into d lambda. You substitute for nu and d nu in the above equation. We have this equation in terms of wavelength. Epsilon of lambda d lambda will be equal to 8 pi h divided by c cube. In place of nu, we have c by lambda cube, that is nu cube. into 1 divided by e to the power hc by lambda kt. For nu, you have to substitute as c by lambda, e to the power hc by lambda kt minus 1. And for d nu, we substitute c by lambda square into d lambda. Then collect all the terms, you will get the energy density in terms of wavelength is equal to 8 pi hc divided by lambda to the power of 5. Okay, so lambda square, lambda cube, you will get lambda to the power 5 into 1 divided by e to the power hc by lambda kt minus 1 into d lambda. So this gives the energy density in terms of wavelength between the range lambda and lambda plus d lambda, and this is called as Planck's law of radiation in terms of wavelength of radiation. So here you can conclude energy density is inversely proportional to lambda to the power 5. That is very important. Energy density is inversely proportional to lambda to the power 5. That is one of the important concept you can derive from the Planck's law of radiation. So this is giving you the concept of Planck's law in terms of frequency and in terms of wavelength. So Rayleigh-Jeans law and other things we'll consider in the next class.